Okay, so welcome back. The next lecture is power electronic circuit analysis methodology. In this, there are only 4 main points, but it's not very short. First, let's see the definition. Okay, the first one is about power electronics. The division here is static conversion of energy to be realized. Static conversion here means we only consider at the steady state. Let's say we have a device that converts energy. So the input can be current input, and voltage input. It should be voltage first. Then output is the outputs are voltage and also current. So the device has some certain functions in order to convert different level of voltage and current from here to different level and voltage, level of voltage and current at the output. Let's say the waveform of voltage and current here like this. Let's say something like this, and then it's from this part we call it a steady state. Okay, and this part is transient. So steady state it means it repeat the waveform repeat itself forever. Okay, but for transient maybe you start from zero. Everything start from zero before you switch you turn on the switch to operate it. During this period is very short time. We don't need to care it. We only care at the steady state. So that's why we call it a static conversion. Energy type. There are 2 types of energy: direct current and alternative current. Okay. Direct current means voltage and current. If only in one direction. Let's say voltage or current here and time here. The waveform can be any waveform, can be sine wave or can be square wave. Maybe draw different like this. But only on one side, in the positive side. So this is DC, direct current. And for alternative current, you can have negative part. Okay, so direction of current can be positive and negative, or can have the form like this. A type of converter studied in this course are AC to DC converter, sometimes called rectifier. Okay, DC to DC converter still called the same like this, but it has particular name for different type in here. We have like direct converter, indirect converter, and so on. And the last one, converter that convert from DC to AC, and it's also called inverter. Okay. And the last definition is switch function. So switch means you can turn on, turn out, allow current to flow from one branch to another. Okay, something like that. And a switching allows commuting between 2 operating sequences. So in this case, you can see the K1 off, K2 on, and then K1 on, K2 off. and one set of operation is called sequence. You have sequence 1, you have sequence 2. In some period you operate from sequence 1 to sequence 2, and in some period from sequence 2 to back to sequence 1, or something like that. Okay, so a set of switch. Okay, set of switch at a certain period is called operating sequence. And here you you will see why we need switching power electronics. Can we have a different way of converting power or transfer power from input to output? First, look at here a linear regulator, which is actually very useful for small electronics. You have a circuit board, a motherboard, then you need power to supply for all those electronics to be properly functional. So actually you just need a linear regulator to guarantee the right level of voltage all the time. But in high power it's not useful. Why? You're gonna see here. Let's say you have input voltage V in and you want V out. This is output for your load. So you need a certain of control in order to guarantee the voltage V out is always stable, okay, and constant. Let's see example. Like in computer motherboard, some part you need only 5 volts for electronics. Some part you need 12 volts for motor to spin CD or something else, right? For the hard disk also has motor, so it needs 12 volts. So of course you have the highest voltage like 12 volts, but then you also need 5 volts for other electronics. So you need certain of regulator. This regulator is gonna control it to have output like 5 volts, and let's say V in 15 volts. So from the calculation here, the efficiency the power of the output divided by power of the input, or voltage time current for the output, and this voltage time current for the input. Because all circuit is in series, current input and current output are the same, right? So you can sell this out and this out, and you just got the ratio between voltage of output and input. And from here you can see that efficiency only is 33%. Let's say you have you want to use this kind of device for converting 100 kilowatt, so you lost 33 kilowatts. So big, so it's not applicable for high power. Then you need switching in order to lower the power at the output. You have big power here, but you want to transfer just a little power instead of giving all the power, but some part absorb in order to guarantee low power at the desired output there. You switching to give little by little, something like that. So you're gonna see switching function. For example, here say you have a input voltage here, and you want to reduce the voltage at the output by half, let's say. Then you just need to switch like this, switch to give full voltage 50% of the time, and then switch to supply zero voltage 50% of the time. That means you only release 50% of the power to there. But it doesn't mean the input spend the full power and output receive half. It doesn't mean like that. I mean the input itself just release only the 50% and the output receive almost 50%. So actually for this kind of switching function used for power electronics, you can achieve efficiency up to 95%, 98% compared to 66.66%. See, you gain a lot of energy. You save a lot of energy, not gain, but you save a lot of energy. And in order to have a smooth power, in terms of curve you say it's smooth, but in terms of power you say not fluctuation of power. You need to use filter that when you release excessive of power, some storage elements store some energy and allow the load to get the right amount of energy. But then when the source does not release much energy, the storage element will compensate to the load. So this kind of function is called filtering. Okay, so filter in something you transform the fluctuation from this form to be just slight fluctuation. Okay, so filter out the high fluctuation. And here is the inductor. It's a kind of energy storage that can store energy in the form of rotating magnetic flux. Rotating magnetic flux, just like rotating a flywheel. Okay? If you have a big metal like a flywheel, you spin it. First, when you spin it, it's hard to spin. It resists. Okay? The initial resist, not want to move, not want to change the movement. But when you give it more and more, it spins faster and faster. Then when you want to stop it, it doesn't want to stop. Okay? Inductor also the same. When you supply energy in the form of current here through the wire, and then it creates magnetic flux inside this winding. This magnetic flux just spin inside. This is a special material that allows magnetic flux to flow easily. Okay? So it spins faster and faster, so it can store energy. Like flywheel store kinetic energy. This one you can say store kinetic energy of magnetic flux spinning. Capacitor can store potential energy in the form of charge. So you need these two. Capacitor need to be connected in parallel with the load, and inductor need to be connected in series with the load, because inductor try to maintain constant current, right? It resists to change the current, right? The larger the value of R, the more resist in the change of current. For capacitor, you use it to maintain voltage. So the larger the capacitance, the higher it can resist the change of voltage fluctuation. You got it? So here is the whole idea, and So this is just a concept that okay, you want to switch from to a low current flow this brand and then flow this brand, but then you need to how you can construct a switch using the power electronic component, power electronic switch to have such function. So for example, here you use one transistor and one diode. When this one is on, high potential here we push this way, but this one block it. So no current flow here, but current only flow this way, right? But after then you switch off this one because the energy storage in here, also energy storage in here, especially for this one, it has a spinning, so it still continue spinning. It means it still push the current to flow this way. Yeah. So that's why even though you turn off that the voltage from the input is 0, but this one still have current continue to flow. Yeah, so this is the whole idea for power electronics. But then yes, you need to learn some way to analyze. So especially here you need to understand some concept on switching characteristics. Let's say we want to we want current commutation from switch 1 to switch 2. This is switch 1 and this is switch 2. Let's say you have a certain circuit that when you switch on for the K1 and switch off K2, then current can flow like this. And then you switch off K1 and switch on K2, and then you can have current flow like this, let's say. Right? Just like this one. This one can block sometime, and sometime it can allow current to flow like this. Right? And so let's see some terminologies and notation. For the second one, sequence 1, K1 is on, K2 is off. Then if you look at, okay, let's see here first. Current IK1 exists, so current can flow this way, but current cannot flow this way. How about voltage? Voltage for K1, when this one is on, current can flow freely. There's no voltage across these terminals, right? And for VK2, this one is off, so the pressure or the voltage push here, and then it's blocked here. Then the voltage here is the same as voltage here, right? Because this one pressure goes through here, through here, through here. When I say pressure, I mean potential. And potential here, here. So let's say here is plus, go here, go here, go here to here, and minus here, still here. So you have voltage here as V, right? For the sequence 2, you change the switch. This one to be off and this one to be on. So current IK1 0 now, and IK2, because your convention is that current flow this way for this branch, and you have convention that current flow this way. Then it means current IK2 equal to minus I, right? Because this one is off. It means you have series here. So current here, in the absolute term, must be the same as current here. And then voltage for the VK1 is the same as V here. And this is just graph to illustrate you move from sequence 1 to sequence 2. At the sequence 1, you for the IK1 versus VK1 for this one, right? For the sequence ones, let's say this one. You have current I and 0 voltage, and then you move to current to sequence 2. I drop to 0, but V sequence 1 I like this, should be here, and voltage 0, so voltage 0 here, and then this point, and then sequence 2, for VK1 current drop to 0, and VK1 as V here. But how do we know it go this way? Why not this way? Because there's no full screen? Full screen. Where is the what happened? Oh, it doesn't display. I don't see any. What happened? Why it crashed like this? How about this one? Oh, I lost all the figure. No control Z because it automatically closed the application first, and then I opened it again. Okay, it's back now. Okay, and full screen again. That's for in another slideshow. Then I need to use duplicate. Yep. Okay, so actually there's no such moment that the voltage would be 0 and current also 0, right? Because if you turn on, current must flow, voltage must be 0. If you turn off, voltage must exist. So you can't go this way, you only can go this way, right? So it's kind of like voltage increase from 0 to certain value, and current drop from this value to 0. So only this way, not this way, because there's no a moment that this 0 voltage and 0 current exist, right? Not possible. And similar analysis, you can get this one. I don't need to go into detail. and also for this. So let's move to the next slide. And here again you have two branches, and one of them is can be driven to be on or off. So this symbol represent that you can control it to turn on or to turn off, right? It doesn't mean this is diode, okay? It just because now we don't say that we employ some particular components. Just say this brand you can turn it on and turn it off, and this brand you cannot dry it. It can be turned on or off by the circuit force itself to do so, right? So general approach for the turn on characteristics for the driven, turn on this one 0 voltage, turn on. This is driven. Turn on, it means can flow. I guess this is I guess it should be like this. Yeah, like this. Right? Because when this is on, then no voltage, but you have current. So this is like reverse. And how about the spontaneous branch? When turned on, because voltage you can supply from here. This one is this current here. Like this. This one, the color is green, so the green here should be, this one is off. Then if this one is off, then the voltage, where voltage here, and current is 0, and then it where from here to here. So this on, this one from here. We need to see off. When it turn off, for the IK, the one that we can control here. Yeah, the red one is the one that we can control. Oh, so it's like the sequence from on to off. This one from on to off, but this one is sequence from off to on. That's why you can see like this, right? From off to on. So off it's here, on the state is here. So off to on. That's why on here mean like this. Before on, it was off, so now it's on. That's why you got from here to here, right? And this one, now it's off. Before that, it was on, like this. So you have from here to here. And you have design, or design depends on voltage, how you apply voltage, whether positive or negative, so it doesn't matter. Okay, next about protection. Yeah, this is very important. Turn on protection. Look at here. For K1, initially turn off and then you turn on. So when off, current is 0, and when you turn on, current will flow, right here. So from off to on. During this period off, during this period on. Okay. For K1, current is 0 when it's off, when it's turned off, when it's on here. For K2, I should say off, on for this one and this one, from on to off, right? Like K1 and K2. Okay, voltage like this. Without protection, you can see that it jumps sharply from 0 to maximum, or you drop from maximum to 0 in absolute term. Okay, in absolute term, it dropped from 0 to from maximum to 0 very sharply, like step. This is without protection, and in many cases, it's gonna break down your components.
How is the K2 turning off if the current is higher?
K2?
Yes.
Here is 0, but this is negative. Okay, but I said in absolute term, from maximum current to 0. Yeah. So with protection, you want current you want current to increase gradually and not sharply. And how you do that? You need to use filter element or storage element like inductor or capacitor. But also you need to be careful when you use this storage element, especially with source. Okay, let's see this kind of protection before get to this one. Okay, so this one about turn on protection, and this is about turn off protection. So here you can see K1 initially on, and then you turn it off, so the current drop from maximum to 0. So when you turn off, you want the voltage to gradually drop, right, across this terminal. How you can do that? You need to have capacitor in parallel. So voltage does not drop sharply but gradually, like this, or drop gradually or increase gradually. Yeah, so this parallel means parallel for all of these two branches. And another one, you need to be careful when you connect storage element with source. If you have voltage source, this one current source, please avoid connect like this. You avoid parallel between source and capacitor. Parallel between current source and capacitor. Why? When you switch on, what happened? at initial state, capacitor behave like a zero resistance component, right? Because it has no charge. So when you put you give the current source in parallel, when you connect, it allow current to flow as much as the source can provide at the initial stage. So it's going to burn your capacitor. When it's full, no, not only in initial state, but actually, I see. You know the behavior of current source? Yeah, the behavior of current source is that, yeah. The behavior of current source is that it must regulate the current always I1 out of its terminal. So at the initial stage, this one behave like a zero resistance. Okay, zero resistance. This one is some resistance, right? Some value of ohm, and this one is 0 ohm. So all the current will flow through capacitor, but not through this. That's why at the initial stage, large current flow through here, and it can destroy capacitor. So capacitor can block the current when it is fully charged, right? Why I say so? Consider a water tank. Let's say you have water tank like this, and you have capacitor. Capacitor has certain of storage, right? Like this. So let's say you have valve here, and you have water up to here. So the pressure represents voltage, calculated by the height. So when you don't have water in here, when you turn this valve, you get water flow through here. Until you have water full up to here, the same height, and then no more water flow from here to here. So they happen the same thing with capacitor. So when it is empty of charge, and you turn on, and current flow all to here. So it behave like zero resistance as long as you can open the valve as big as you can, and it flow fully, right, to this capacitor, to the storage. Can you see? Oh, very small. I don't know how to make it bigger. That's why I prefer to use not full screen. It's hard to see the pointer. If I can remember all the time, I can press control, it's okay. But cannot. Another type of circuit is that you have, oh my goodness, this is, yeah, right, it's okay. This is current source, correct? And this is voltage source. Well, if you have voltage source and you have an inductor in series with the load, what happens? Previously, I said it destroy capacitor, but actually it destroy the switch itself because current is too big. Destroy the switch itself. The switch is, but maybe it depends on the toughness between capacitor and the switch. But mostly here we are talking about protecting the switch. And here, for this one, you have inductor series with load, and you switch on this one. Oh, sorry, this is to protection for. No, it's dangerous when you switch off. Yeah. What happens when you switch off this one? When it's on like this, yeah, you have some other circuit, maybe other resistance, then current can flow like this, right? But then you switch off, what happens? When you switch off, what happens with the voltage? Of course, current is 0 here, but what happens with the voltage? Because in inductor, it's kind of a storage element that store spinning magnetic flux. So first, when it was still on, current flow only this way, but this one there's no current at all. So it's like you have a flywheel that is at rest. When you switch off this one, the current is trying to flow through here, right, from here to here. So what happens if you it's like you have a big flywheel and then you have like a motor that you supply voltage at max speed, and then it tries to spin the flywheel too much. It's like this. Okay. Well, not so good. This is flywheel. Let's say it has a hand, something that you can push. Yeah, just simple concept. Okay, let's say this one has. I don't need to draw it very detailed, right? Maybe just make between schematic and 3D. Let's say you want to spin this one, but you do two way. One is you use your hand to push on this one little by little, right? But another person come, I want to push it because I want it to spin as fast as it can in short time. You push like this. Which one is which person get hurt? Yeah, the third one get hurt at the hand. Why? Because the flywheel, the inertia behave like a resistance, and it doesn't want to move. But if force it to move, you get hurt. And here also, the magnetic flux inside inductor doesn't want to spin. But if you force it to spin too much, the voltage increase at the terminal too fast. The voltage increase sharply. That's why you can destroy the switch. Okay? Even though you have small resistance, right? You have small resistance, that means that if only resistance, it could be, if only resistance, the voltage may be just the same as voltage in here. But if you have inductor, voltage could be even higher when you implement switching. Why is that? Yeah, because voltage at here, let's say VL is L di over dt, right? L di over dt. What if the change of current is too much? Then the voltage at the terminal is very high because it's proportional to the derivative. Okay, so we don't like change sharply at the terminal of inductor. Can say that. You should you should give power little by little to inductor, something like this. Okay, so this is how you protect your switch if you have current source and voltage source like this. Let me verify here which one is current source, which one is voltage source. Yeah, I think you are right. Yeah, I think you are right. This one should be voltage source. So it's like this. This one should be current source. Because after I analyze it, then it's something strange. Because if this is voltage source and you have zero resistance, then current is very big. That's why it can destroy the switch, right?
What is the difference between voltage source and current source?
Current source means you have a certain of device that it always gives the same amount of current, no matter what your load is. You have big resistance or small resistance, whatever, it always try to give the same current. So this one is some kind of control current source. There's some this device constructed with control system.
So it is a device.
Yeah. So why I know that this must be current source, because I look at this formulation. If you change current very much in here, then you get so big voltage.
Here, can you use some example of current source?
Current source, you just have feedback control. You measure the current, and then so you can have like large voltage source, and then you have device that can measure current, and when the current is not the same as the current at the set point, it just try to give more voltage, like that. Yeah, so this one must be current source. Any more question? What Dom? Any question? So now here, how you can link components in power electronics converter. If you have voltage source, so no, it's clear, right? Here is voltage source. Yeah, if you have voltage source, you need to use inductor in series, because inductor resists not to allow current to flow too much when you have voltage source. To simplify things, I choose the easiest condition. When this one is on, you have relationship V L equal to voltage Kirchhoff voltage Kirchhoff law, voltage here and voltage here must be the same, right? So VL and V1 must be the same. And then VL, you have relationship LdI over dt. And then you can have, because this is constant, and then you have I equal to V1 over L integral dt from 0 to, you can call this tau, and then 0 to t. So you can have current increase gradually from 0 to a certain value, not jump sharply, right? And when it turns off, the energy stored in here will release to here. So actually this one is called boost chopper or converter. Yeah. And for this one, you implement switch and protection like this. Yeah. So here you can call it as filter. At the same time, you implement it correctly to protect, to have switch protected, right? And this one is called buck converter, but I will explain more detail later in the next lecture actually. Buck converter. Yeah. Boost converter means you can have voltage V2 at the load higher than voltage at the source. And buck converter means you have voltage at the load lower than voltage at the source. Okay. Yeah, the next point is going to be some sort of analysis. Yeah, we still have 10 minutes. And so in power electronics, when you design or you analyze your circuit, you use method of assumed states. Assumed state means you assume the sequence or you assume the state of switch, whether it's on or it's off. So you assume different case and you make analysis all the cases, and then you verify which case there's no violation on the function of each component. Then it means your assumption is correct. This one is very, very simple. You have a diode. You construct a rectifier. This one is called half-wave rectifier. Not quite half-wave, it's just very simple rectifier. Then, okay, first you need to know the property of a diode. What is characteristic of this diode? First, diode can sustain positive voltage or not. Let me ask you, diode can sustain positive voltage or not? You need to understand the term sustain. Can it sustain positive voltage? It means it can maintain positive voltage. It means it can maintain potential this side higher than this side. This is anode. This is cathode. Can it maintain potential on anode higher than potential on cathode? Can it? Okay, let's see what happened. So you take a yes, I take a no. Yeah, you put the voltage like, well, let's say we have resistance. Okay, resistance is something like this. So in this case, diode allow current to flow, right? When current flow, it means ideally there's no voltage across this terminal. So it cannot maintain positive voltage. It cannot sustain positive voltage. Because in this case, it allows current to flow. But in reality, it has, we call voltage dropout, like 0.6 volt or less. But we just consider in the ideal case, let's say it's 0 volt. Okay, 12 volts here. When you put that and then you measure voltage in here, there's no voltage. Okay, so now you know it cannot sustain positive voltage. How about current? Can it sustain positive current? Sustain positive current. It means it can allow current to flow in positive direction. So in this case, current can flow in the positive direction. I think maybe you got confused my question. It can sustain positive current, but it cannot sustain negative current. I mean, there's no current in this way. There's no current in this direction, even though you reverse this polarity. Right? There's no current in this direction. It blocks. So it cannot sustain. So be careful with the term sustain. Maybe you say maintain is better. Is it clear? Right? Clear? Yeah, some of you from electrical engineering department, right? Okay, then we can draw curve for diode like this, voltage versus current. Here, it cannot sustain positive voltage because it will always turn on. Cannot sustain positive voltage, which means like this. If you supply positive voltage, the voltage is rather 0, and you can have current like this, right? And then it cannot sustain negative current because it turned off, which means voltage is there, right? If you reverse polarity like this, voltage here and voltage there is the same. Yeah, 12 volt here, or roughly 12 volt here also. It's not exactly 12 volt. So this curve is called characteristic curve of diode. You never get the curve at this side or at this side. Never, right? So when you assume the state, whether it's on and off, and you calculate, because you have just normal circuit, you use voltage, a Kirchhoff voltage law, Kirchhoff current law, calculate, and then you get the current or voltage at the diode, and you construct the curve, and then you see that if the curve is here or here, and then you violate the condition, it means your assumption is wrong. You understand it? Okay, just a simple case. Yeah, this is just process. First, I assume the state to be on or off, and then calculate voltage current from the linear circuit theory, and then you verify, you check whether there are any violation. For example, you see that a diode has negative current, that is wrong. Or you can see that the voltage across the diode is positive, it's also wrong. Then on violation, yes, this is violation. If there's no violation, you can finish your analysis because all your assumptions are correct. If still there's even one violation, you need to assume new set of states and go on to step 2 maybe, because new set of state, which mean already passed 1, right? So go back to state 2. State 2. Maybe I should change. Very simple case for the rectifier. When the source is positive, they have value positive, and you assume that the diode is off. When you calculate, for sure that you can get the positive voltage on the diode, then it's wrong. And when the sign value is negative and you assume that the diode is on, you assume the diode is on, you will get negative current, right? Yeah, when this one become negative, voltage here negative, because this is AC. When sign value is negative, and you assume this one on, so you calculate that if it on, it can conduct negative voltage here, then you get negative current. It is wrong. Yeah, this is just one component, one resistor, that it's easy to calculate it immediately. But if you can even you already know that whether it's on or off. But this is just a way to explain the process. Sometimes you assume it incorrect. Yeah, assume it incorrectly, then you calculate voltage and current from a linear circuit theory, and then you will see violation on the characteristic. Yeah, this is just the idea for analysis. So I finish my lecture now, and see you next week. Step 2.